If not, bummer. Bummer for the people that aren't here. Okay, so your formula sheet on here has the probability of an event, number of outcomes divided by sample space, the statistical probability, which is empirical probability. It kind of tells you what it is on there anyway. Shut that door.
Shut it really obnoxiously fast.
Stare at them.
Yeah, come on, guys.
All right. So we have the probability of event, the probability of complement, and then it says the and probabilities, which is the probability of A and B is equivalent to the probability of A plus the probability of times probability of B given A, right? Yeah. Probability of A times the probability of B given A. And then it says the probability of A and B, if they are independent, would be the probability of A times the probability of B, if they are independent. So what can you conclude if things are independent? Well, that these things would be equivalent to one another, right? The probability of B given A would be the same as the probability of B, right? So it kind of has a roundabout way of telling you what the test for independence is, but it doesn't directly tell you. It also has the OR probabilities on here. Probability of A plus probability of B minus the overlap minus probability of A and B. But again, you'll get this on tomorrow's quiz as well as the Chapter 3 test. Just so you guys know, we'll take our quiz tomorrow, and then we will do Section 3-4 on Wednesday. I will give you the test review on Thursday. Obviously, no school Friday or Monday. Except for me, I got to be here on Friday. If anybody wants to come and hang out on Friday, I'll be here. So no school Friday or Monday, and then we will review again on Tuesday. We'll go over the test review, and then we will have our Chapter 3 test next Wednesday. All right. So describe the difference between theoretical and experimental probability. Provide an example of each. Describe the subjective probability. Define simple event, independence, and mutually exclusive. I'm not going to write all this stuff out. Let's just talk through it. Theoretical probability. Remember, theoretical probability is like not doing any sort of like experiments or anything like that. Just the theory behind it. Just the total number of outcomes that I could possibly have as a success. Number of outcomes that I could possibly have a success divided by total number of possible outcomes. That is the theoretical probability. The difference between theoretical and experimental probability. Well, experimental then turns into I have done some sort of research. I've done some sort of project. I've done some sort of, and now I can tell probabilities based off of that thing. That is experimental probability. I've done an experiment. Provide an example of each. Kind of done that. Theoretical probability is like rolling a dice, right? Experimental probability is if I take a random sample, asking somebody of something. I can then say I can predict if I choose one more person what they would say on that same question. Okay. That is experimental probability. Subjective probability is when your opinions come into play. We had that one question about like the what's my target breakdown. Not necessarily based on experiments or anything like that. Not based on theoretical, but just your subjective probability, what you believe is going to happen. Define simple event. Remember, a simple event is when I only have one possible outcome. One possible event that could be a success. Independence, remember we just kind of talked about that. Independence being the probability of one does not affect the other, right? The probability of A does not affect the probability of B. Okay.
I would need to make it to at least turn that in.
I appreciate you turning that in.
Yeah.
I think I have to write you a pass. Okay. Perfect.
So much.
I'll be posting this video.
Thank you.
You'll hear this thing in the video too.
Oh, great.
All right. A simple event is when only one outcome can occur. Independence, again, probability of A not affecting the probability of B. And then mutual exclusivity. Remember, mutual exclusive means that two events, there is no overlap, right? There's not the possibility of them happening at the same time. Like drawing a king that is also a 2, right? Those things are mutually exclusive. All right. So let's take a look at our contingency table that we have here. I'm going to get out of sheets. All right. It says use the chart below to answer the following questions. If I choose someone at random, what is the probability that I choose someone who has been to another country, given that they have been to the beach? So we see this contingency table. I'm asking, have you been to another country? And I can answer yes or no. And have you been to the beach? And I can answer yes or no. And I even got the totals there for you. So if I choose someone at random, what's the probability that I choose someone who has been to another country, given that they have been to the beach? So this is the probability of country given beach, right? Probability of country given beach. Okay, country given beach. So beach, yes, is my totals, right? Beach, yes, is my totals. Given that they have been to the beach, 115 total people. Got it. That's my divided by, right? And my numerator is that they have been to another country. 10. That make sense? 10 out of 115. Remember that you should always reduce down fractions, or just give me the decimal. 0.087. And I always like to round it to 3 decimal places. 0.087. Assuming someone has never been to the beach. Assuming someone has never been to the beach. So this is probability of something given no beach, right? What is the probability that they have been to another country? So yes, country, given that they have never been to the beach, right? Another conditional probability. Okay, so now I say no beach. No to the beach. Yes to the country. So that's 30 out of 85. So given that they've never been to the beach, what's the probability they've been to another country? That is yes country out of the total people that have been no to the beach. 30 out of 85, which gives me 0.353. Again, if you see any discrepancies or you're like, why'd you do that? Please stop me along the way. Part C here. If I choose 2 people at random, what's the probability that both students have been to the beach and have traveled to another country? Well, what's the probability of one student going to the beach and traveling to another country? Move this out of the way. That would be yes, right? What's my denominator? 200, right? It's 10 out of 200. Because this is out of everybody, I choose, okay, what's the probability? The first person, 10 out of 200. What's the probability of the second person? Now, I've already chosen one person. So how many people are left that have said yes? There are 9 people left that say yes. Out of 199, right? You've got to think about the conditional, right? I have not replaced that person. If I choose 2 people at random, it's probably that both students have been to the beach and have traveled to another country. So first kid I select is 10 out of 200. Second kid, 9 out of 199. Okay, so that gives me 90 out of 200 times 199. That's a really small number. 0.002. Well, we'll just round it to 0.002. Yeah, a 0.2% chance of happening, because that's a very specific set of conditions, right? If I have 200 people in a room, and I know only 10 of them have said yes, what's the probability that both of them I pick? Yes, that's a very small chance. Are traveling to another country and traveling to the beach independent? Now, this is a very specific thing here. You cannot use your opinion. This has to be a mathematical definition of independence. Okay, so this is the probability of country. Is it equivalent to the probability of country given beach? That's what we are testing, right? That's what we are testing. I could also test probability of beach if it's equivalent to the probability of beach given country, right? That is an equivalent test for independence. You'll lead to the same conclusion. But let's take a look at this one. Probability of country at random. Probability of country is yes to another country. 40 out of 200. 40 out of 200. Let's see if it is country given beach. Did we just do that? Yeah. 10 out of 115. Well, this was 0.0, what was it? 0.087 or something? Yeah, 0.087. And 40 out of 200 is not 0.087. It is 0.2. So we can say that these things are not equivalent. Now, when I say that they are not equivalent, what does that mean? Independent or dependent? Dependent. If you can say that the two probabilities are equivalent, that means that one does not affect the other, right? So that would be independent. So since I have these as inequals, these are dependent. Dependent events. And again, there's no opinion on that, right? I didn't use my opinions based on, the probability of somebody traveling to another country or not, right? Those things are dependent, mathematically dependent on one another. Okay, question 3 on the bottom here. In a survey of Lake High School seniors, 90% of the students said they owned a smartphone. 3% had a dumb phone. Dumb phone meaning not smartphone. This was, it's funny. It's even like a year and a half back. I feel like more people have smartphones. Anyway, and 7% didn't own a phone at all. You guys know anybody that don't own a phone? No way that's actually said. Yeah? You do? Of the students who own a smartphone, 60% owned an Apple. If you were to pick one of the seniors in the survey at random, what is the probability that your selection owns a smartphone made by Apple? Okay, so what we're going to look at here is a smartphone made by Apple, right? That's our goal. Well, in a survey, smartphone, probability of smartphone and Apple. Okay, now in terms of my formulas, okay, that is equivalent to the probability of smartphone times the probability of Apple given smart, right? Well, what's the probability of somebody picking at random and getting them a smartphone? 90%. What's the probability of an Apple given smartphone? Well, of those who owned a smartphone, 60% owned Apple. Isn't that Apple given smart? Right? So there's our conditional probability. Everything is given to us. I don't have to do any sort of fun calculations. 0.54 is my probability. If I pick a person at random from these students, there is a 54% chance that I pick someone that has a smartphone that is also an Apple. What do you actually think that probability is? If you took the entire senior class, you picked somebody at random, what's the probability that they have an iPhone? 70-80%. I would say that's pretty high. All right, questions on that? See, now that, what is that me saying that? What type of probability? What type of probability would that be? No. Like when I say, what do you actually think it is? Oh. Subjective probability, right? Because we're putting our opinions into it, right? This, what is this? That's experimental, right? I have done a survey and I am finding data on that survey and then making my probabilities based off of that. Okay. Theoretical wouldn't really make sense in this situation, right? It's not like I can, I don't know. It's not like rolling a dice or anything like that. All right, number 4. Flipping it over to the back. Consider a standard 52-card deck of cards with the following problems. Now, remember, in a standard 52-card deck, there are 4 suits, 2 colors. Remember, we have 13 cards in a suit. 4 suits, 52 cards. What is the probability of randomly selecting a 2 or a heart? Okay, so the probability of 2 or heart. Okay, from my formula sheet, 2 or heart is probability of 2 plus probability of heart minus probability of 2 and heart, right? Follow me there? Probability of 2 or heart is probability of 2 plus probability of heart minus the overlap, 2 and heart. Okay, how many 2s are in a deck? 4. How many hearts are in a deck? 13. Right? Minus, how many 2 of hearts are there? 1. Okay, so this is 4 plus 13 minus 1. That is 17 minus 1, or 16 out of 52. And I'm going to reduce that. 16 out of 50. Oops, 52, not 25. And that is 30.8%. So 0.308. That's the probability of randomly selecting a 2 or a heart. What is the probability of selecting a 5, replacing it, then selecting another 5? Okay, so what's the probability of the first 5? How many are there? 4 out of 52. Now, because I replaced it, the probability of me selecting that second 5? 4 out of 52. Without replacement, well, then it would turn into 3 out of 51 on the second draw. So 16 out of whatever 52 squared is. Really small number, 0.006. 0.006. So a 0.6% chance of selecting a 4, putting it back in, and selecting another 4. Or 5, excuse me. What is the probability of selecting a 7, not replacing it, then selecting another 7? Now that is what we were talking about just a second ago. There are 4 7s in a deck. But if I take one out, I do not replace it, there are 3 out of 51. What should happen to the probability? Should it get smaller or bigger going from B to C? Smaller, right? Because there's less of an opportunity in the second draw. Still very similar. I would get 12 divided by 4 times 3 is 12, divided by 52 times 51. And that is 0.005. So as expected, the probability decreased. There's less of a chance of me pulling that second 7 because I did not replace. Let's take a look at number 5 here. 4 people purchase a TV on the same day with identical circumstances. The probability that the TV is faulty is 0.02. Right? So there's a 98% chance that the TV is all right, but there's a 2% chance that the TV has something wrong with it. What's the probability that all TVs are faulty? Okay, first person would be a 0.02. Then it would be 0.02 for the second, 0.02 for the third, 0.02 for the fourth, right? So this is 0.02 technically raised to the 4th power, which is a really small number. So 6 zeros in front of it. 1, 2, 3, 4, 5, 6. 6, 7? No, just 6. 1, 6, actually. Yikes. 1, 6. It's almost 0, right? It's almost 0. Can I say that it's 0? No, because there's no possibility. Right? What's the probability that none of the TVs are faulty, right? That none of the TVs are faulty. Well, what's the probability? This is the probability of good and good and good and good, right? 4 times over. So that's 0.98 times 0.98 times 0.98 times 0.98, right? All 4 of them are just fine. So 0.98 to the 4th power gets me 0.922. 0.922. So there's a 92.2% chance that all the TVs are just fine. What's the probability that at least one of the TVs is faulty? Okay. Now, remember, this is 1 minus none, right? At least one, we got to remember that. At least one is always 1 minus none. Oh, please. Hey, James. Hi, James. Let me get you a quiz real quick.
All right. And also a calculator.
What? You didn't bring a calculator?
I got yoinked.
That's a new word for stealing. All right, here's my calculator. I'm gonna put you in the hallway. Let's see where we can put you. Oh, another person. You want to take a quiz too? We're going to do stuff. You can watch a video after. Yeah, because that goes to the video. If that's up to you. Don't do that. That's fine. I'll see you then. Okay, so again, at least one is 1 minus none. At least one minus none. Now, remember that we have to be a little bit careful about what is none in this case. So that is 1 minus the probability that none are faulty, right? Probability of none faulty. What's the probability that there are none faulty? 0.922, right? 0.922. So this is 1 minus 0.922. 1 minus 0.922 is 0.078. So there's a 7.8% chance of at least one of them being faulty. Questions? And again, that is not the same as all of them being faulty. People always confuse that. The all with the at least one. Yeah. Questions there? Cool. This is the one that people get hung up on. At least one. Just try to remember. At least one is 1 minus none. All right, number 6 here. Left on my papers back there. Right? After a study, it is shown that 15% of students like English, 10% like science, and the probability that a student likes both English and science is 0.004. Are the events liking English and liking science mutually exclusive? Mutually exclusive. Make a mathematical argument. Obviously, do not use real life experiences. So, remember that mutual exclusivity, and you can kind of think about it in terms of the formula sheet kind of tells you, because the probability, let me show you this. This is on the formula sheet. The probability of A or B is equivalent to the probability of A plus the probability of B minus the probability of A and B. But if the probability of A or B, if these events are mutually exclusive, then this turns into that, right? So what am I saying here? If mutually exclusive, then the probability of A and B is 0, is nothing, right? Because that goes away here, right? If they are mutually exclusive, the probability of A and B is 0. It cancels out. So let's take a look back at this question. I want to see is the probability of English and science equal to 0? Well, I want to do this. I'll put a question mark up here. Is that equal to 0? The probability the student likes both English and science, I mean, it's really small, but is it 0? No. The probability of this is 0.004, which means that these events are not mutually exclusive. If they were mutually exclusive, then the probability of both of them happening would be 0, right? That's the idea of mutual exclusivity, right? That the probability does not, that there is no overlap. So if there is a possibility of overlap, these are not mutually exclusive from one another. So what is the probability of randomly selecting a student liking English or science? So the probability of E or science is equivalent to, so I'm just going to go straight to my formula sheet, the probability of E plus the probability of science minus the probability of English and science. Okay, probability of English is 15. Did they shut my door?
Yeah.
Perfect. Thank you. Probability of English is 15%, so 0.15. The probability of science is 10%, so 0.1, minus the overlap of 0.004. Okay, so 0.15 plus 0.1, which is 0.25, minus 0.004. So we have 0.246. Questions about that? Again, don't use your preconceived notions. Always use the mathematical arguments for both independence and mutual exclusiveness. Mutually exclusive. And again, the formula sheet kind of has a roundabout way of telling you all those things. And number 7, this is our last one, right? What's this here? Oh, whatever. Oh, this is more of those same problems. A lock has a 6-digit passcode, but you've forgotten it. You know the first 3 numbers were odd, and there were no 1s in the passcode at all. How many different passcodes are there? Okay, so how many digits do I have altogether? 6, right? Okay, so I always like to make myself a little diagram. 1, 2, 3, 4, 5, 6. And see how many different possibilities. Well, you know that the first 3 numbers were odd. Okay, so that means 1, 3, 5, and 7. So those are my possibilities here. 1, 3, 5, or 7. 1, 3, 5, or 7. 1, 3, 5, or 7. Do I know anything about the last 3? Well, I know that there were no 1s. So this can throw out this guy, and this guy, right? So I know there's 3 possibilities here, 3 here, and 3 here. Do I say anything about repetition? No. You know that the first 3 numbers were odd and that there were no 1s. Okay, so how many different digits could I have here? 9, right? What's wrong? Why did I forget 9? I'm just realizing that. 9 is no longer an odd number. What are you talking about? Okay, so. Yeah, I do know even an odd number. Right? Now, how many different possibilities for my last 3? 9 of them, right? Yeah, because I just can't have 1. It could be 0, right? 0, 2, 3, 4, 5, 6, 7, 8, 9. So I have 9 different combinations or 9 different outcomes in those last 3 times. All right, so that is 4 times 4 times 4. Oh, 4 times, come on now, times 4 times 4 times 9 times 9 times 9. All right, that's going to get me my total possible. 46,656. 46,656 combinations. Questions about that? So there's your quiz in a nutshell. Oh. Hey. Yeah. Sounds good. Questions about that? We good here? Yeah? We feel good about our quiz tomorrow? Easy peasy? Cool. All right. We can have a little bit of time to relax. We turn off the